Well, good morning, ladies and gentlemen. I'm Bob Savinsky, and it's my pleasure to chair this first session on thorium reactor physics. I'd like to thank the hosts for a tremendous dinner yesterday evening. Lots of very good food and very good wine, and I'm actually surprised to see that anybody's here this morning. Thank you for getting up and coming along. The first speaker in the session is Ganesan from BARC, who's going to talk about nuclear data development related to the thorium uranium fuel cycle in India. Thank you.
Thank you. So, good morning, everyone. It's a great pleasure and a professional honor for me to address this distinguished audience. I have been working in this field during the last 44 years, and originally I joined the department as a fast reactor physicist. We were building the Rhapsody-type reactor in Kalpakkam in collaboration with France. Of course, after '74, that collaboration stopped, but we continued and built the reactor. And I was in the design group. Very early in my career, I realized that the nuclear data program is a very important component of any serious nuclear power program. And I had to struggle to show to the department, but now, today, at the end of my career, I am retired now, but I work as an emeritus professor, as a prestigious Rajaramana Fellow of the Department of Atomic Energy. I am also a professor in Homi Bhabha National Institute, and I have PhD students with me working on various problems in science. I am a scientific consultant to the Office of the Principal Scientific Advisor to the Government of India, New Delhi. Now, what I am going to take you through is a quick tour of the way in which a phase transformation took place in India. The leadership recognized, though belatedly, that nuclear data is very important. And since 2004, thanks to this phase transformation, we have made phenomenal progress in nuclear data physics. One of my friends, Professor Otto Schwerer from Germany, told me, "Das ist unglaublich," that we are doing so much. So I am going to go through that. And my friend Jean-Pierre Revol invited me in a very timely manner, and the BRC people encouraged me by buying my flight ticket. So I'm very grateful to these authorities, but for whom I wouldn't be here. And I would like to skip many of the slides. I have 99 slides, but I'm going to skip many of them because they were covered by my friends. What I want to say is that our program, three-stage program, many people don't believe that it is possible. We are talking of uranium-plutonium fuel cycle. We are talking of natural uranium PHWRs. And we are talking of fast reactors. We are talking of thorium-uranium fuel cycle. And believe me, we are talking of long burn-up course. And we are talking of closed fuel cycle. Even rich countries would be afraid to say that, but we have been sticking to our guns during the last 60 years. There has been no deviation in terms of commitment, either by the scientists or by the government. We are very lucky that our parliament believes us, and they have been continuously giving us salary. And for me, in the last 44 years, every day of going to BRC and working was a day of great excitement. It's a dream profession. So this was again covered by Professor Vijay, and since I am retired, I am giving you the official websites for you to look into. So I will skip this. You know all this now. An Indian situation, as I mentioned, this has been covered by many people, and Dr. Degwekar will be covering again on accelerator-driven system. But in my talk, I will mainly focus on the nuclear data science activities. And we all believe that despite Fukushima, for an energy-hungry country like India, it's a viable option. And we have closed fuel cycles and multiple fuels and high burn-up. And I must say here, nuclear data for thorium cycle, though the title says, there is nothing like working only for nuclear data for thorium. You have to work for nuclear data of all the elements in the reactor at all times and states of the reactor, even at the later times of the reactor life. Range of actinide fission products. And what are the challenges we have faced in Indian nuclear industry? Nuclear reactor is a physics machine. It is not like something you can make a car and give it to somebody to operate. Physicists have still a great role to play despite 60 years in designing the best nuclear reactor design. In my opinion, the best nuclear reactor design is to be made. I believe that the generation N, we are talking of generation 3, generation 4, this N, I don't know what it is, 8 or 9 or 10, it should be not even remotely be accident prone during the entire fuel cycle, across all the fuel cycle activities, with minimum radioactive waste, with maximum tolerance of normal and even remotely possible operator errors. This is yet to be made, we all know. And here comes the role of multiphysics, multiscale modeling, M3 with the big data science, and nuclear data forms part of that, apart from other properties like thermodynamic properties, corrosion, and things like that. This is a letter which was signed by Carlo Rubbia in 1993 and sent to Hans Blix. And he appreciates the nuclear data services, which I was doing when the energy amplifier was just in the beginning. I got a phone call from the same people, Jean-Pierre, what is the energy of the neutrons coming in the end-to-end reaction in strontium? What is the energy distribution? I realized that they must be doing something very new. They were also particle physicists. They were not familiar with the neutron transport tools and software and data. So that was very interesting that someone who thinks originally wants data. But the reactor scientists in India said they know everything we can design. But if you are doing new things, new materials, and if we don't repeat the same type of reactor, nuclear data is very important. And it gives a better scientific basis. It was in 2004, the nuclear data program was declared as a major thrust area by the Department of Atomic Energy. And I'm going to say why it happened. And we have today established many faculty people getting involved in nuclear data centers. We fund them in a coordinated research program within the country. The Nuclear Data Physics Center India was born. But it is still a virtual center. And what are the activities we do? We do measurements. We do compilation and evaluation, which people thought it is a very low-level work and should not be done. But we are phenomenally successful in that. We are having several DAE, BRN sponsored meetings. After 2004, I myself was given a blank check to conduct about 20 meetings at the national level. And we encourage people in all the advanced reactor applications to use the best data. And we have coordination with the IAEA. And I'm very happy to say that we are also part of the CERN NTOF program. It is a very important program, it's a cutting-edge technology program, and it should be continued over the next decades. And the identification of the faculty is a continuing process, and students' recruitment and so on. We are making very rapid progress since 2004. Of course, we need to do a lot more. We are still in the lower part of the learning curve. And we are also encouraging all our nuclear physicists to put their data into the IAEA X4 database. It was not available before. People published papers, thought they were glorified with the authors' names, but they were not really spending time to put the data into the IAEA database. So when you click the IAEA database with a mouse, our graphs, the graphs that were generated were not showing Indian contributions. Now there is increased visibility. China has made about 200 entries since 1975. It's amazing. They have been doing it since 75. We got up in 2004, we woke up and we have made about 250 entries in the last 6 years. This is what Professor Otto Schwerer was saying. This is unglaublich, you can do this. And we have initiated a lot of base technology efforts to start Indian evaluations of data. We have not yet done generating our own recommended values of data, but believe me, we are going to spring surprise by doing all this in the next couple of years. And we are also going to the covariance error matrix in a very serious way. We will be having one workshop in December. And India is now a select band of countries which is making the criticality benchmarking to the ICS-BEP International Handbook, published by the international agencies like the US Department of Energy and the Nuclear Energy Data Bank Paris. The database was not available to India before, but after we contributed Comini, we insisted we should have official access to all the 4,500 benchmarks, experimental benchmarks, criticality, we got them. So it is officially, we are using it. But we still have to percolate down this, culture of benchmarking to younger generation, which we are doing through sensitizing by workshops. And also the digesting methodology of covariances in nuclear data, I will come to that again later. These are all some of the workshops on covariances, December 16 to 19, surrogate reactions and in applications. We are almost becoming a leader in this. And there is workshop on evaluation of nuclear structure and decay data, which is basically propelled by Dr. Gopal Mukherjee in Variable Energy Cyclotron, Calcutta, and Professor Ashok Jain in IIT Roorkee. I was involved in creating a project there. So basically, generically, we have got 5 base technologies. The physicists are not very interested in doing this, but engineers understand they are important. And people like me who have been interacting with engineers right from day one, Dr. Paranjip, father of fast reactors, he was able to appreciate the importance of data. We had a small section to process the data files available from the IAEA. So generically, you have these following 6 items. One is the physics experiments, then putting them in a computerized format so that you can computerize and post-process the data for evaluation purposes, and also see the discrepancies in the various scatter and data. And then evaluation means, evaluation is a term highly misunderstood in India. People think running a computer program is evaluation. Evaluation means finding the truth in the scatter of the data. We are always in continuous search of truth as scientists. And we use Bayesian theorem, statistical tools, and so on. India is just getting into this field. We are having the 3rd workshop in December. And cross-section processing, we have been doing traditionally right from beginning. We were very intelligent users of the INDB database, right from the early 70s. And integral experiments, we are concentrating. We understand that ultimately, nuclear data is only one component. Fabrication uncertainties are there, tolerances are there. and experimental uncertainties are there, and how to reduce the number of integral experiments. I will come to that. Then ultimately, the software and use of covariances to define error margins due to uncertainties in nuclear data. People do not know that these first 5 steps are not visible to the reactor physicists. They actually start with a plugin library and a code, and they think that that is a major part of the design work. But actually, this is several orders of magnitude efforts before you come to this level, running a lattice cell code with a plug library. And this involves several decades of work sometimes. Now, ND, Nuclear Data Physics Center of India is a dream come true for me, and it is a virtual mode at this time. We hope to make a transition to with permanent assets, building, and so on, but it will take time, but people are working on it. Historically, we were generically oriented, historically in user-oriented approach. Now we are graduating to be a contributor to nuclear data generation, not just users of handbooks and recommended data. And the first nuclear data file was created by me in 1984, when the IAEA launched a project for evaluation, but that work stopped afterwards. It was a Thorium, first Thorium file from India, which was put in the international format. Hans Lemmel from the IAEA coordinated that, and this was presented in Uppsala at that time by me. We also have an MOU with the IAEA to mirror all the databases. We use all the online data services. And India is the only country when the IAEA mirror site is down, IAEA original website is down in Vienna, people access our website to access all the data. From all over the world, we get hits in this, and this is one of the interesting things which is being shown to the young people, to tell them that whatever you do, please use the best recommended data. Don't just use old values and think that you are right. We also participated in the WIMS library update project. India was traditionally using the library that came with the WIMS code, and we wrote our own WIMS code, but we were users of the WIMS library, but not the WIMS code. We could write our own, the lattice cell code. But then the data part was kept stagnant for until 2004, when we created this project. I was involved in creating this IAEA library project, and we succeeded to produce updated libraries, put it on the website for everyone to use it. I will come to the use of this later. And I'm just trying to show you, when the IAEA did this project, we created a software to automatically plot over 100,000 graphs comparing various reactions. This is one typical graph for eta of uranium-235. How did the eta of U-235 change in the last 40 years, in the last 30 years? This is the curve which shows. And generally what happens, the reactor physicists show this curve and say data has not changed. It is a logarithmic plot. Everybody says fine, everything is fine. But eta is a very sensitive quantity. So here the ratio is plotted for the same graph. And you can see that in the thermal region, in the bomb region, there is a very good agreement. The ratio, it is 0 difference. And then in the in-between goes to plus 25% to minus 15% for eta. So if you have systems like ADS and you design, the first paper by Kapoor used the old WIMS library. I used to tell him. And the problem is that 96% of the reactions occur and there are cancel-off errors, and you adjust the cross-sections to fit the integral experiment, so it's working. As long as you stick to that system, it works. So it is very important to realize that nuclear data was not well when reactors were operating. The nuclear energy was introduced to mankind without adequate knowledge of nuclear data. And the improvement of nuclear data over a function of time is a continuing effort. And we also participated in the evaluated nuclear data of nucleides with the thorium uranium fuel cycle. And I was the person from India nominated by my department to work as the chief scientific investigator. In the previous one, I created that WIMS library project with the help from the IAEA. There also I was the chief scientific investigator. And this has produced very good evaluated data files, and it is endorsed by the end of 7 people. There are reports available I'm giving for reference. Coming to the measurements, we didn't have neutron source, so I requested my colleagues to explore the possibility of using lithium-PN reaction, and they responded very fast. Because once the department has said it's a thrust area, it's important, all the physicists who were earlier reluctant to make measurements came forward and said, okay, we'll do. And here you use a proton beam, and proton hits the lithium, and neutron is emitted, and the neutron is hitting another, the sample target for which you want to measure the data, and you have a monitor. It's a ratio cross-section by offline gamma counting. And very good papers are published. For example, this is a thorium N gamma point, and this is a Mega BK is the first author. She is a PhD student from Bombay University. And she used to come and tell me, sir, I am doing this work, and people are saying I would never get a postdoc, but she is now a postdoc in Duke University. So it is nothing like nuclear data is not a frontline work. It is a frontline work, but how you do it with high quality, that is very important. All my students who have done PhD under me, they have got postdocs, whoever wanted it. And then these are the new measurements of India. There are no measurements previously, the first time we have made. And you can see this, this was published in the European Physics Journal. And this is very interesting, and this has come in the international wall chart of the 2013. Protactinium 234 has a 6-hour half-life, and there is no measured data available. And we separated Pa233, some nanogram, and we irradiated in the Apsara reactor. And Pa233 does not fission in thermal region, but in situ Pa234 is formed, and that has a huge fission cross-section of around 5,000 bonds, and we could see the fission tracks due to that, and we inferred that cross-section. And this has been accepted, and it has come in the international wall chart. And this is by Professor Nayak, who is now in Korea on a visiting professor mission, and he has done this neutron activation of thorium, this one. These are all the measurements of thorium end-to-end performed by various students. These are the points which we have generated. But you can see here the year, 2012, 2007, 2011. So previously, nobody measured the end-to-end cross-section, though we have been talking about U232. But I insisted. Then there were a lot of arguments. If already somebody has measured in some other country, why do you want to measure it again? Then I tell them it becomes an abstract quantity for you if you keep taking the value from outside sources. At least once you measure, then you know what it means. It applies to everything like viscosity, specific, anything. And here you can see that these are the measurements. For capture, this MT102 is the ENDB6. And these are the recent measurements. And there was a measurement in 1977 by Rakesh Chawla, who is a professor in Switzerland, in EPL, nuclear engineering. And this is again the cross-section which we have measured. These are all the points measured by India for the thorium N-gamma. And resonance region, we don't have the neutron time of flight facility. We are establishing one at Kalpakam now. And this is again for the end-to-end reaction. And most interesting thing is, we developed a new method for measuring data of unstable nuclei. You cannot make a target of an unstable element. Regulatory Commission also will find it difficult to allow you to put it in the apparatus. And this is an interesting example of the innovative nature of Indian scientists. And we use the TAFR facility, and we measured the cross-section of Pa233, which has a half-life of 27 days. We measured the fission cross-section of neptunium-239, which has 2.35 days, neptunium-240, 61 minutes, plutonium-240, which has 14.325 years. That decays to americium-241, you know. It should be 241 here, there's a mistake. Now, how did we do it? You do not have a neutron beam, you do not have a target of an unstable nuclei. How like a magician you do this? Use of surrogate nuclear reactions. We had a 2-day workshop. What happens here is, the desired reaction is neutron plus Pa233 forming Pa234. The neutron is not available to me, Pa233 is not available to me, but what I do is, I take a lithium-6 beam, bombard it on thorium, both are stable and available, and then I produce the same compound nucleus. Then using the Bohr's compound nucleus model theory, and getting that branching probabilities from the experiment, you can get the this thing. Now, this is the same thing I told you, the surrogate reaction. Now, the thing is that you can change the lithium-6 to lithium-7, and you can change the target thorium to U238. So it is all depending, and then you can get other combination. This is exactly what we did here. We changed the lithium-6 and lithium-7, so with the U238 target, and we could reach neptunium-240. So we plan to go to all other higher actinides and make measurements, and all these papers were published, peer-reviewed and highly appreciated. There is a American Journal of Physics article. I don't know, I'm having it here or not. This is the one by Jutta Esther, and she quotes the BRC paper in, I think, around 20 places as a new hybrid approach. And this is one of the things I am very happy to say that our nuclear physicists were thrilled to measure. And this is the measurement which was published in the Physical Review, but when we went to the XFAR, we found that there were some silly mistakes. One mistake was the binding energy for the last neutron in protactinium-234 was taken from the old handbook by the nuclear physics people. I also overlooked it. So that shifted the energy. When we fed into XFAR, this mistake was corrected. And then there is a small difference in this height here, because the people in nuclear division casually used to 233 by 233 plus 1, which is the factor for transferring from lab to center of mass frame. They took it as 1, because this one. So this is the problem. So that corrected, and XFAR data is a correct one. These are the papers published. I will skip this. Again, this is the Pa234 paper, which is 6.7 of. These are our new data. There is no data. This is the first time data in the world that is from India. It is naturally because these are all things which we are doing in a very big way. I mean, it's amazing. One of my colleagues said our activities have increased by a factor of 200 in the last in nuclear data. But I would say when you have done nothing and you want to do all this, it looks like a huge thing. Then compilation again is a big thing. We had a very unique managerial initiative, and we collected all the people for 4 days, and they were reading all the papers, experimental papers, sitting and noting down all the points and making the XFAR entries. And there was no looking back from 2006. We had one in 2006, 2007. This kind of thing, I don't think advanced countries, economically advanced countries also can do. We have a demographic advantage, and we have budget for working lunch and so on. And it is really very exciting, because the senior scientists who measured data were very happy that 4 or 5 people were sitting together and entering their data in the IA database. You can see people are all there. This is just a typical photo. We were invited because of that by the select band of the 13 countries to join them as a member of the International Nuclear Reaction Data Network. India became a member for the first time in September 2008. Indian flag started flying. Before that, we were not allowed to join because we were not doing the compilation. Now, because of this, there is increased visibility of nuclear data physics work, nuclear physics work in the world, and there is an increased scrutiny on the quality of the work. So you can't escape just by saying, I have published a paper, I'm great. No. And this is the actual graph. You can see here about 25,000 experiments are there. And India has contributed about 250, starting only in 2006. Many countries have started much earlier, but their values are much lower than this. But it doesn't mean that we have, it's a competitive or overtaken. It's simply that we also covered all the old papers. Some of the pioneering papers by Professor Raja Ramanna on the fission angle, fission distribution, fission neutron distribution in U-235 fission, they were all covered in the X4 entries. Okay, now let me come to the very interesting example why this 2004 gave a phase transition in thinking on nuclear data. We had an operating PHWR, and there was a small incident, and the reactor power rose to a high level from 73% to 100%, and it was declared as level 2 incident by the IAEA on the ENS scale. That means that there is no damage to the operator or to the public, but we do not understand the reactor behavior with respect to the design manual. And basically, the steam generator authority scrambled it. I don't have time to go through all this, but what happened was the design manual did not predict this. Design manual predicted that when temperature rises, the reactor would go down because there is a feedback coefficient negative, but the design manual was based on 40-year-old nuclear data. And at that time, I had just in a timely manner, due to blessings from God, the IAEA WIMS library update project was sitting with its results on the website, and someone in the Nuclear Power Corporation took that data and redid it. He exactly fitted this curve. So overnight recognition came that even the design manuals of operating reactors will have to be continually updated every 10 years. You cannot be static. This is very important because you have so many nucleides and nucleus data is being improved. It's not that everything was known when the reactor was first operating in the 50s. And we have the very interesting case of thorium loading in PHWR. This was due to the very bold initiative by Kamala Balakrishnan and Kakotkar. There's a paper in '94, and they predicted that you could use, instead of depleted uranium, there are some thorium bundles to do power flattening. And this was done in many reactors. Vijayan also spoke about it. And we later also published a paper in 2009 using the current genetic algorithms, and there are about 50 loadings possible. And this one, which these people have evolved, this pattern is one of the patterns. It comes out in that study. And this was also published by my PhD student in Annals of Nuclear Energy. Now the point is, after 508 full power days, after 4.8 years of cooling, 5 grams of the bundle was taken out, and the U-232 was calculated by the origin code, and there was a factor of 6 difference. So basically, there was a 6 to 8 factor of under-prediction in U-232 when you run the origin code. But the origin code has thorium data to interpret these results, but the thorium is supposed to be I need at least one more minute. Yeah. So when we reanalyzed it, and we could remove the discrepancy by a proper data thing, and this is now the current situation. I will skip further. I have only a couple of minutes. And I want to say that U-232 prediction is a very important thing, because you are talking of neutrons above the 6 MeV, and this is your fission spectrum. There is a lot of uncertainty, and this is what gets moderated in the neutrons. So getting the flux above 6 MeV is a challenge in reactor physics calculation, and convoluting it is with this curve in this region, and getting the U-232 is really a challenge. And then in the case of ABTR, you have got a nickel reflector, and therefore there is a neutron facing the threshold, below the threshold energies. And then in the fast reactor, Pa231 cross-section is also lower, and you know the accumulation potential of U-236 is more, so the production is much lower. And I don't have time to go through all this. I was trying to say that nuclear data is one of the uncertainties, but there are uncertainties in composition, geometry, numerical approximation, so on. And this is one of the curves which showed for our AHWR how the void reactivity voiding from normal operating conditions to different data sets. So if you say my design is giving negative value, it is with the ENDB American set, you may be thinking that everything is fine, but when you change a data set, it goes to positive. It was published in the Nuclear Science and Engineering Journal by my PhD student, Umar Shankar, who is also my colleague. And coming to the India joining the criticality benchmarks, we have made the Kamini, Purnima 1 and Purnima 3. Each one took about 3 years' time, and 5 of us did about 1,000 calculations for each of these, by taking the uncertainty of each of the things that occur in the reactor, nuts and bolts, including composition, impurities, and so on. This is really a Bible document for all these three. And one of the things I want to share with you is in this Kamini reactor, one of my students, this is an operating reactor, there is a BEO, massive BEO reflector, and she made a calculation by mistake, heating only the reflector to 1200 degree Kelvin, and it was coming to 1.03. And we found out indeed that when you increase the temperature of the reflector but not the core, there is a 23.8 milli-K upside swing. This is because the scattering cross-section for the below 4 electron volt increases with temperature, and it scatters better at higher temperatures. This is very well established in terms of theory, but it happened with such a high magnitude, positive high temperature coefficient for differential heating of the reflector, because when you remove the reflector, the BARC core has a K effective of 0.55. It's a highly reflected thermal system, and this is again in the multi-group same data. And we understand why the reactivity goes up. It is a new effect. I have not yet published it. People told me you publish in Nature and so on. I didn't do it because it will create unnecessary panic just post Fukushima. We have to first measure it and see if it really is there. So I have told the Kalpakkam people to do an experiment. And this is the very old thing which I presented in Marseille in 1990, international conference, FISOR conference. And I have changed the various data sets only for thorium and U-233. And the doubling time changes from 57 years to 107 years. That is the sensitivity to doubling time to nuclear data at that time in 1990. Even today, there will be a big variation, but I am looking for a student to redo these things. And then I will quickly go through. This is the americium-241 criticality. It is varying from 55 kilograms to 300 kilograms based on how you do this. This is americium-240. That is 241. 243 is going 1824 gram to 150 grams. You see, the differences are very large. This is protactinium-231. The K effective is 2.19 in one publication, another one is 0.97. Then Pa233 is this. Again, the previous value 1.8, our value is 1.4. These are benchmark values, and you can see there's a huge difference. Now, I have published a paper showing that U232 goes critical, and it goes critical in 3.63 kilograms. Sorry, this is over. Oh, it's done. Something I have pressed. So 3.6 kilograms of U232 can go critical. I would like you to look at this paper. And I also mentioned about the proliferation resistance climbs on U232. And thorium-230 called ionium, you have to make sure that it is not present in thorium-232. Thorium-232, we assume it is 100%, but if it is mixed with the uranium ore while taking the ore, the uranium-232, some of them would have decayed to thorium-230, and you can get a maximum of 11% of thorium-230 ionium in some of the samples. So you have to watch out for that, because that will produce a lot of U232. And I could not go to the last slide, because that is an appreciation of how French people have generated 75% of the electricity by having one-to-one mock-up experiments and then adjusting the cross-sections. Though our cross-sections were not known, there was a difference of opinion between this school of thought and the American school of thought. They said it is God-given numbers, you should not adjust it. But as long as you keep to the same adjusted cross-section, same codes which you have cancelled the errors or done the mistakes, and same method of fabrication which has same composition, same tolerance, and so on, it works. That's how we could do the reactor design. Thank you for your patience.
Thank you very much indeed. Well, I think we have time for one or two questions. Yes? Have a microphone, please.
What was the cross-section you measured for protactinium-233 2NF?
Oh, that was about 4,800 bonds.
Beg pardon?
4,800 bonds.
4,800 bonds.
Bonds.
Then what's the point in separating protactinium-233 in molten salt reactors? Because you leave it there at fissions.
Well, you have to see, first of all, Pa233 has a resonance, it goes to Pa233. All these have to be studied. We have not studied the implications of that in the reactor. And also it will depend on the high flux reactor, it will behave differently. So I have a feeling that a lot of new physics have to be studied taking all this data into account.
Implication is experiment that shows that protactinium survives. It doesn't disappear in the molten salt reactor. So therefore, I don't understand this.
See, the Pa233 is present, not Pa-234. Pa-234 is formed when Pa-233 captures a neutron, and Pa-234 has a half-life of 6-7 hours. It is a very small, very rapidly decaying. During that short time, if it fissions, then it fissions with a high probability. That's what it means. So many reactor physicists may feel that this number is not relevant for the actual design, but when you have new concepts, all this will start playing a role. If you have a high flux study you want to make, at that time all this will play a role.
Okay, just one more quick question, please. Yes, over.
Please, can you tell us what is the maintenance cycle of the Kamini reactor?
Maintenance?
Yes.
It is operating and is doing very well. We are using it for neutron radiography and fuel.
Yes, but about the maintenance, how is it loaded from time to time, the repetition of the loading?
There is no very severe burn-up there.
Yes.
It is not a high burning rate. It's a 30 kilowatt research reactor. So,
yeah, so for instance, today it is working.
it is working today.
And it will be working until when?
Oh, that's an issue. Actually, they may have to load the fuel once the reactivity goes below the value. So right now, I think it is just reaching the break even. That's what I heard last month. So there is a possibility that they may upgrade or they may decommission. I do not know the real situation. Yes, sir.
May I ask a complementary question? Where did you get your uranium-233 to load Kamini, and how much kilograms? How many?
Well, everything was done indigenously, and it's 600 grams.
Sorry.
We radiated thorium in our research reactors.
Yes.
And we learned how to separate. It was done in India. It's totally indigenous. And 600 grams of U-233 material.
Okay.
Yeah.
Okay.
So,
Okay. Thank you very much
time.
indeed.
And the full document running to 200 pages is available from the ICSBEP handbook, which spans all the experimental facilities around the world. We have contributed that.
Okay, thank you. I think we should thank Dr. Ganesan again. Thank you.